Thank you very much for giving me opportunity to give a talk here. Um, I have been working on protein structure modeling and recently working more towards the cryo-EM, modeling for cryo-EM. And today I'll show you several new things we have been doing recently. So there are many computational tools used in cryo-EM structure determination. And so we have at Purdue, we have two good brand new cryo-EMs. And what we do is that, okay, from the 2D particles, there's computational methods needed to build the 3D density map. And then what we work on in my lab is to build the 3D structure from the 3D map. So we don't currently do a 2D to 3D or everything all together. We do a 3D density map to the 3D protein and other structures. There are several methods to model protein structures. Well, classically, you could identify the secondary structures, or you could do the rigid structure fitting, and also the de novo modeling. De novo modeling means that you don't use explicit protein 3D structures, existing structures, but to build the model, structure model, by looking at the density directly. Now, as you know, that the number of the cryo-EM maps determined and deposited in EMDB is increasing very rapidly. This statistics is about a week ago. So we have now 22,000 the maps in EMDB. And another thing we wanted to pay attention to is the resolution achieved in each year. So when we have started to work on cryo-EM, which was around 2016 and 17-ish, as you see, that resolution at that time is around here. So about 1/3. So this is the 8 to 10, and then this is from 4 to 6. So here, about the little over 1/3 of the maps are between 4 to 10 angstrom. So first we started to work in this range, and then recently more and more higher resolution maps are determined. And so recently we work more closely on better than 4 angstrom. So for the range, resolution range for 4 to 10 angstrom, the deep learning can work very nicely. So here, this is in 2019 publication. Well, when the resolution is around 6 to maybe 8, you can see that as you may know, the alpha helices, a beta strand in part of the maps, probably when the local resolution is a bit higher than the other part. But if you apply deep learning, you can see those secondary structure more clearly. So okay, so this EMAP to secondary structure, EMAP to seq we developed is a very straightforward application at that time to identify the secondary structures from cryo-EM density map of this range. So what it does is you have cryo-EM map, it scanned the map by this box. The size of the box was 11 × 11 × 11 angstrom cube. And so what it does is it scans it. Then at each position, each box position, it identifies alpha helix or beta strand or coil or other structures at the center of the box. In terms of the architecture of the deep learning, it's a very simple convolutional neural network. But the one thing we added is that we added the second neural network here. So this receives the original probability value detected by the initial convolutional neural network. This first convolutional neural network gives you the probability of alpha, beta, alpha helix, beta strand, or coil for that box. And then the second neural network takes that probability value and further refine it. we can see that the results at that time. Well, once we applied it to the simulated map at 6 angstrom and 10 angstrom, well, as you know, the simulated map is too clean compared to the realistic the cryo-EM maps. Well, so if you apply this this EMAP2-seq to the simulated map, the accuracy of overall accuracy to detect that the secondary structure is almost 80%, over 80%. Now, when we apply it to the experimental maps, so here x-axis is the resolution of the maps reported by the author. Y-axis is the accuracy of detecting secondary structures. When the resolution is up to between 5 to 6 angstrom, then the accuracy is over 80%. So the accuracy doesn't drop that sharply relative to the map resolution. Up to about 8 angstrom, well, the accuracy is maintained around 60%. Occasionally it's higher. When it comes to the 9 to 10 angstrom, this is a very, well, by eyes, it's very difficult to see the secondary structure at this level. Now, at this range, it depends on the map. Sometimes the accuracy is still very good, but in some maps, it's not the deep learning cannot see the specific features much. Here's some example. This is the proteasome. In each panel on the left, I'm showing is the cryo-EM map and also the authored structure. And on the right is the detected secondary structure by this deep learning method. And then the color is the magenta is alpha helix, yellow is a beta strand, and here are the resolutions. So as you can see that the secondary structures, well, just by visually, you can see that the secondary structure patterns agrees relatively well. The accuracy is in those examples, accuracy is around 70%. And sometimes even like, okay, so for example, here, we can also see the alpha helix connecting these two domains very clearly. And we think if you have the structure to fit it to the density, secondary structure detection could guide you to fit the structures. We can also extend the methods to include DNA or RNA. So now in EMAP2-seq plus, the plus here is addition of nucleic acid, DNA or RNA. Okay, so that is last year, 2021. Idea is same. You have cryo-EM map, you scan the map with a box, and then now, in addition to alpha, beta, and coil, we also predict DNA or RNA, so which is shown in cyan. So the architecture is based, the two-step architecture is the same. First, we predict from the first neural network, it predicts the probability value of alpha helix beta strand or other structures in proteins or nucleic acid. It is difficult to distinguish RNA and DNA because there's only one, basically only the OH groups difference between in the sugar ring in the DNA and RNA. So then after the first neural network predicts output these probability values, then the second neural network will further refine it, takes that probability value, and then basically makes the final decision. In terms of the architecture, this time we use ResNet blocks. This is the type of the blocks in convolutional neural network. Other than that, basically it's same. Now we can see some examples. Here, this is the nucleosome. So the cyan is DNA wrapping around those protein complex. Now C is a gyrase, which unwind the DNA. So here the DNA is in the middle. The deep learning detects this DNA very well in the middle. The other part, the two ends are predicted as a different structure. Maybe a protein prediction get a higher probability, but in the middle are very nicely predicted. Now this is the overall detection for this gyrase. As you can see in this case, you could even see the secondary, the alpha helix, the cylinder really well, very clearly. Now D is an interesting case. D is the TF2D. And at the very beginning, this structure was, the map is determined at 8.7 angstrom. I think this is from Eva Nogales' lab. And at this resolution, the authors did not fit the structure of this region because of the low density. And then later, they determined the same the structure at 4.5 angstrom. Now, and then at that time, they provided the fitted structure in this region. But if you use the deep learning, even at 8.7 angstrom, you can see the secondary structure pattern relatively well. And it turned out this secondary structure pattern agrees well to this later determined structure in this region. This is the results of the benchmark. So here, A is showing the overall accuracy of 4-class classification. Here, classification for a box is alpha helix, beta strand, or coil, or DNA or RNA. That is, that is why the Q4 accuracy on the y-axis. X-axis is showing the map resolution. So, and then here, the cyan are showing the DNA and RNA detection. Interestingly, well, the nucleic acid can be detected, position of DNA, RNA can be detected very well, even at very low resolution, 8 to 10 angstrom. Actually, the detection accuracy does not drop much. For overall accuracy, well, has the same trend as the previous version of EMAP2-seq. When the map resolution is 5 to 6 angstrom, it was about 80%. And after that, it's around in the here in this example, in this results, about 50%. But if you are only interested in 2-class classification, proteins or nucleic acid, then we can see that the protein can be also very well detected. This panel C is same data, well, using the same results as panel A, but now we consider it as 2-class classification, DNA, RNA, nucleic acid, or proteins. So with this neural network, actually the proteins are also very well detected. Actually, the confusion which dropped this Q4 accuracy was the confusion between the secondary structure within the proteins, but proteins and DNA are very well predicted. This B is showing how effective the second neural network is. So this is x-axis, the results of the phase 1 network and the first neural network. The second neural network is, as you see, the improving most of the cases. There are some cases which are deteriorated. Those are the the coil regions, or some maps in the beta strand was overwritten to a wrong secondary structure assignment in the phase 2, the second neural network. But most of the case, almost all the cases, the second neural network was successful in refining the results. Now, okay, so that was the resolution up for map resolution for 4 to 10 angstrom. If you now use neural network deep learning for higher resolution map, you can now start to see that the amino acid types or C-alpha positions. And here in our recent publication, it was, I think this appeared about a month ago. So we applied this deep learning for detecting potential errors in the protein model. So it's a deep learning based amino acid residue-wise quality assessment score, DAQ score. So idea is now, so here, now that you input is the density map and the protein structure model. And then from the cryo-EM map of resolution up to about 5 angstrom, so as usual, we detect secondary structure types, alpha, beta, or coil, and also amino acid types, 20 different amino acids, and then also the C-alpha positions. And then basic idea is that we compare that probability values coming from the deep learning against the protein structure model, and then check if they agree or not. And if they don't agree significantly for many amino acid in a row, it's highly likely that the assignment could be wrong, and it worthwhile to check. So we can look at how the score is computed. So okay, so here amino acid type score for position I is computed in this way. So in numerator here, suppose you have a model, protein model, and you have tryptophan at position I. So the numerator here is a probability from a deep network, neural network, that tryptophan here locates in this position. Now, this is the normalized, the denominator is tryptophan being everywhere. So if the tryptophan signal at that position is higher than average, then you have more than one in this in the parentheses, and if you take log of it, you have positive score. So if you have a negative score for that amino acid, that means that the amino acid assignment you made there is less specific than everywhere else. So although we are using deep learning here, so this has a well interpretable meaning. So we can a little bit talk about the data set we use for training this neural network. For training neural network, we use the maps of between 2.5 to 5 angstrom, and it's over 1 million those boxes of 11 × 11 × 11 the size. This is same architecture as we used in EMAP2-seq+. And we made sure that those data sets are non-redundant. Here, by non-redundant, I mean that two maps we used have no similar proteins, even one protein pair between any two maps. If two maps have at least one protein sequence, a protein with 25% sequence identity or higher, then we removed one map from the data set. For deep learning, it's very critical to make sure that you make a non-redundant data set, because deep learning is powerful enough to learn everything from the training set. And if you apply to the similar test set, you get very good results, but it's not generalized enough. For the benchmark data set, we applied this the methods into on the 3 benchmark data set. First one is the PDB entry from cryo-EM map, which have 2 versions. So occasionally, the authors deposit first PDB entry to the PDB, and later revise the structures and then provide the updated version. And we use that to first check our score, and later we applied it to many PDB chains massively in PDB. So here, this is an example of how DAQ score behaves. So in this example I'm showing is PDB ID 7JSN. In this case, actually, there's 2 versions of PDB entries, and author have changed the structure kind of significantly, and then also put the correction note to the paper. So it is well, probably safe to say that the first structure had some errors in it. So here, this is showing the comparison of the 2 versions of the structures, and then magenta regions are the regions which have significant difference between version 1 and version 2 of the structures. And when we apply our DAQ score to the first version, it complains. So the red regions have a negative scores, which are so DAQ score doesn't like the structure, well, amino acid assignment in these structures. In the updated version, now the DAQ doesn't complain basically almost basically at all in the main domains. There are some still complaints in this region. Now we can see that how the score distributes. X-axis is the position of amino acid position. Y-axis showing the three scores: amino acid score, secondary structure score, and C-alpha position score. And those regions here, well, the different regions are highlighted in gray here. And this region corresponds to the top. And then there are those regions in gray corresponds to these alpha helical regions. So in the first part, this region, which remains as a negative value, even in the second version, is here. So if you look at this region, actually, amino acid score is low, and also the atom score, C-alpha position score is negative value. So most likely, this region probably is the conformation is also could be improved because not only the amino acid assignment, but the C-alpha position has a negative score. In contrast, these regions, alpha helical regions, actually the C-alpha position is not complained much. So this, but the amino acid assignment score has a very large negative value, which indicates that those are the really that the main chain trace is okay. These are the alpha helices, but the sequence assignment may be shifted. So this is a typical situation that the sequence assignment error can happen. We can also compare to other quality assessment scores, including the Q-score, EM Ringer, and Kablam. Q-score and the EM Ringer is basically comparing the density of the map against the simulated density of each atom position and checking the overlap. This Kablam is basically just checking the geometry of proteins, so it's not checking the consistency against the cryo-EM map. It's checking the protein geometry. Now, okay, so if we apply those three methods to the same entry, the Q-score is detecting those regions, especially the first region, which where probably the conformation might need to get attention, and also those three regions. But I would say the DAQ score is detecting those the sequence shift significantly. Other scores are detecting some part, but probably DAQ is more catching the errors more vividly. So here we can consider that the detection as a classification task. Here in the PDB entry with two versions, we can classify the residues into two classes. Those residues which did not change in the second version from the first version, and those residues which are modified, which are corrected probably in the second version. So this is a distribution of the score of those consistent regions which didn't change in the updated structures, and then this is an inconsistent region which are revised in the second version. As you see that inconsistent region, well, most of the residues above have a positive value. For inconsistent region, actually you see that it's more shifted towards negative, and if it is a score is below like -0.5 or -1, actually there is most probably those residue assignment could be wrong, and worthwhile to the double check. And those are the score distribution of the other scores, and then this is showing the accuracy of detecting those inconsistent regions by those 4 scores. Well, this is AUC value and which are used for evaluating classification accuracy. Yeah, DAQ score is doing well relative to other scores. And so DAQ is a deep learning, but it's not trained to classify two classes. It's trained to detect alpha helix, the amino acid and C alpha in the cryo-EM map, and that makes this DAQ score interpretable. This is how the DAQ score, average DAQ score changes relative to the resolution. So here, this is each dot is the average DAQ score of entire structure cryo-EM, in the cryo-EM map. So if the resolution is around 2 to 3, on average, those structures are very well modeled, and the average score of across all of the residues is close to 1. But when the model is from a lower resolution EM map, then on average the DAQ score starts to go down, and when at around 5 angstrom on average, the score is around 0. This means that this does not mean that the structure itself might be wrong, may have some errors, but here when the resolution is low, then the DAQ score start to say that, oh, I cannot see well, there's not enough signal to detect it. So since the DAQ is trained on the map between 2.5 to 5, it's at this point aimed for maps up to 5 angstrom. Yeah, so this is the score distribution I showed you before, and yeah, when the DAQ score is minus 0.5 or lower, or minus 1 or lower, it's likely that the residue assignment could be wrong, and then worthwhile to go back to the structure and check it. So we also analyzed the over 4,000 PDB entries from cryo-EM map. And those are the PDB entries which do not have 2 versions. So well, technically I could not exactly tell if the flagged the residues with negative score is really wrong or not. But if I check the residues with DAQ score with less than -1, so it's very significant low score. There's about 4% of PDB chains which have at least 1 residue with this score. Here's some examples. So here, okay, so I'm showing 3 examples. In this example, so this is the density and then how the residues are assigned. As you see that this phenylalanine is not fitting to the density very well. And then this is complained by DAQ. So now, well, we ran actually AlphaFold to see how the AlphaFold model this structure. And AlphaFold doesn't look at the density at all. It just models structures, but it fits nicely to fits better to the density. And so as you see that, okay, so this protein 11 is now shifted here, which fits better, and this phenylalanine fits better, like here. So as you see, this is just basically the residue shift. The main chain is okay, but the residue shift seems to be happening here. This is a similar story, same story basically. There's 2 isoleucines facing outside to the solvent, which might be, which is not probably usual. But if you do if you check the AlphaFold model, then it fits nicely. Side chain fits better to this density. And as you see here, again, this is a residue shift. There are some extreme example like here, which have the chain entanglement in the model. So the DAQ score is available on the Google Colab web server. You can upload the PDB structure and also the cryo-EM map and then you will get this plot, and then this will tell you which residue have a negative score. We have also analyzed many more PDB entries from cryo-EM map, and we are currently preparing to show the results in this database. Its database is already accessible, and we are making a final check to make sure that we do our best job to provide the results. Now the question could be, yeah, once you detected potential errors, okay, how do you fix it? Of course, you can go back to COOT and then remodel it, but one quick thing we developed is to to use AlphaFold. But the thing is that if you run AlphaFold, AlphaFold doesn't look at the density at all, and then it just modeled the structure from multiple sequence alignment. So you cannot control. And sometimes the AlphaFold does not make a, also, of course, it will remodel everything. So even the very confident regions are remodeled by AlphaFold, which now does not fit to the map that well. So to control, to only AlphaFold, to only let them model that potential wrong regions. We cut the multiple sequence alignment, and also provide the partial template. So here to the AlphaFold, we only provide the very confident region as a template from this OSAS model, and only provide multiple sequence alignment for the local region which have low DAQ score. So then AlphaFold only have the information to remodel those potential wrong regions. We tried some other combinations, but this is kind of a quick hack to AlphaFold to only get the local region fixed. This also have a web server, so you could try that. This is some results. So this is y-axis is the RMSD of after the DAQ refine. The model tested is all below 2 angstrom. Other methods include Rosetta Relax or some Phoenix, the refinement tool. Often does a good job, but not always. GDTHA is basically checking the percentage of correctly assigned residue positions. DAQ refine does a better job than other methods for most of the cases. This is some examples. So the region which have a very low score is now fixed and then get a higher score. In this case, again, this is a residue shift. The main chain itself, the conformation itself is okay, but if you shift it, shifting the residues would fit the density better. This is showing correlation between DAQ score and the quality of the model. So among this, in this study, we tried to run AlphaFold in various different ways, and then which result in the models with different qualities. The y-axis again is the quality. Well, basically the fraction of residues which are correctly assigned. And as you see, that the DAQ score is able to rank the model really well. So so the strategy here is that we build a lot of models with AlphaFold with different type of hacks, and then pick up the one which have the highest DAQ score. So okay, last couple of slides is to show that this deep learning based features can be also used to improve the structural modeling. The idea is that, okay, you have a density map, and then before start to model the structure, we can detect the amino acid atom types or amino acid types, and then secondary structures, and guide the structure modeling. So here we compared this deep learning based deep MAMUS. So we have the structure modeling tool called MAMUS, which do not use the deep learning detection at all. So let me just quickly explain how this main must work. This is a couple of years ago. Here, the basic idea of main must is that first you have a cryo-EM map, and then you identify the dense position in the grid, and then you cluster it, and then you make a graph, and then trace the C alpha positions. So this is totally the density-based automatic modeling process. So if you compare the original main must and then also deep main must, so this now uses the deep learning based features. Then well, TM score is again about the kind of a fraction of residues which are correctly modeled. That we can make a significant improvement over the original main must. This is in terms of RMST. So improvement we can observe, benefit from the deep learning is typically in these two cases. Here in the main must, okay, here green is the correct structure from author, and then red is the trace by original main must, which only trace the dense positions. So in this example, this region here is a density from sidechain. But since main must doesn't know where C alpha is, it often goes through the sidechain density, but that can be nicely corrected by if you detect the C alpha position by deep learning. Here, this is about the alpha helix. If you simply trace the most dense region in alpha helix, it's inside of the helix. So the main must will trace in this red region, like in red, which loses this alpha pitches of alpha helix. But if you detect C alpha position, now the alpha helix is nicely reconstructed. Yeah, these are some examples. We compared it with deep tracer. One is one of the state-of-the-art methods, which also uses deep learning. So this accuracy is showing the C alpha position accuracy and also amino acid type accuracy. So in deep main must, we use the deep learning assistance and also some other alignment methods, new alignment methods we developed, and that increased the residue type assignments. This is similar. This is about, okay, this method, the deep main must can also do the multi-chain modeling. Residue assignment is very high for these two examples. And then this is for two other examples. Now, okay, probably you might, so this is, I think, the last slide. You might want to ask how our methods do relative to AlphaFold. Yeah, AlphaFold do a very nice job in most of the cases, and it's not well. If you compare direct deep main must with AlphaFold directly, actually in this data set used in some papers, we do slightly better than AlphaFold. Right, but actually, if you do this main must method is tracing basically the density. So if the density is very has a locally low, then deep main must cannot do much because there's no signals actually there. But AlphaFold doesn't care. It modeled the loop region very nicely. So if you combine this, if you can kind of stitch take advantage of both methods, then the combined methods can do better than AlphaFold significantly. That's some preliminary results we got very recently. Yeah, so this is showing when AlphaFold can be wrong. In this very simple two domain structures, AlphaFold modeled individual structures very nicely, but the relative orientation of the domain does not agree with the density. And because the protein sequence information at the linker region does not have the specific conformation information. But if you trace the density, yeah, of course you can identify the orientation correctly. So if you combine both, then you have a better structure. The tools are all available on our lab website, and some of them are indexed in SP Grid, and all the source code are made available. So please take a look at it and let me know if there's some problems or suggestions. Here is a DAQ. Okay, so this is done by Dr. Genki Terashi. He's the research scientist in my lab. And then the DAQ score and the EMAP to SIG plus is done by Shao Wan. He's a CS graduate student. And thank you for your attention.
Thank you.